Well, thank you so much, Youssef, for the introduction. I really appreciate everyone coming out today. So today I'm going to be talking about a topic that is seemingly on, the top of everyone's minds nowadays, which is this promise of inference scaling. And more specifically in this talk, kind of covering this question of whether or not we can use classical probabilistic inference methods to scale very small language models to O1 level performance. As Youssef mentioned, my name is Isha. I'm a second-year PhD student at MIT, and I'm really excited to chat with you all today. So the more mathematically intense topic or title of this talk is a probabilistic inference approach to inference time scaling of large language models using particle-based Monte Carlo methods. But the kind of summary is a particle filtering method for inference scaling. So I think the first thing I want to talk about before we kind of dive into the meat of the actual method itself is why there's kind of this emphasis on open models and why people should really care about harnessing their abilities. So the first kind of thing is we know that closed source frontier models like GPT-4 and Claude Sonnet are really fantastic at a variety of tasks. They're really good at math reasoning and logical reasoning and doing your homework for you and lots of different tasks that have been integrated into most people's daily lives. But they have several downsides, as we all know. The first thing is that obviously they're all hidden behind an API wall, which is a problem not just for entire industries like healthcare and education, where those industries are very highly regulated. There's a lot of regulations that's kind of say that you're not allowed to send data to proprietary API models like that. This is a problem not just for those people, but also for smaller entities or enterprises that have sensitive data that they don't want to share with larger entities like OpenAI and Google. So this API wall. Also, there is a company in Malaysia, as I found, that is a construction concrete company that has a literal product called API walls. So do with that information what you will. The second, I think, most major downside of this is that they're exceedingly expensive to run, both energy-wise and monetarily. So if you think about from a monetary perspective, the top 3 rows of the table kind of tell you the prices from very large closed source models, and the bottom 3 rows signify the costs from open source models. And you can kind of tell there's a massive difference between the very small open source models and larger models, just in terms of a $15 for a token, a million tokens versus 70 cents or 52 cents or even 9 cents. This will really add up once you start to scale the amount of queries that you're kind of chugging through the language model. Also in terms of an energy usage, smaller language models can be hosted on a handful of GPUs, while closed source models really take a larger number. So now that we've kind of covered this, the emphasis on why open models is important, now let's talk about what actually inference scaling is. So what is inference scaling? A lot of studies have shown that cheaper open models, even those as small as 1B models, when you query them several times, will actually eventually correctly answer relatively challenging reasoning questions. So obviously, when you query a Llama 1B model just once for every question, your accuracy is going to be a lot lower than your accuracy if you query GPT-4 once for every question. But the study from Stanford that I was going to say came out a while ago, but it was last year, says that as you scale the number of samples here on the x-axis, so this is just the number of times you're querying the language model, the same exact question. Let's say I query a language model 100 times, and if any of those 100 answers are correct, I am giving myself a point for that question. So that's kind of this coverage at pass k on the y-axis. The graph here shows that as you increase the number of samples, the number of times you're querying your language model, your accuracy is really going to scale up very nicely. And so what does this suggest to us, besides the fact that this is a very pretty looking graph? This suggests to us that small language models, they have it in them to answer very difficult questions. You just kind of have to find a way to squeeze it out of them. If the lines had just stayed constant, it would have suggested that language models at scales as small as 1B didn't have the ability to answer these questions. But the fact that eventually with 1,000 or 10,000 samples, at least one of the answers is correct, suggests that now we just kind of have to find a way to get there. So this problem now becomes different than a traditional language model problem, right? A traditional training language model problem would involve how do we take a language model and inherently make it the best model possible. On the other hand, inference scaling is now this question of how can we intelligently navigate the search space that these smaller models provide to find the best possible answer that they have. So this kind of tells you the problem and promise of inference time scaling. Also, feel free to interrupt with any questions at any time. This is a relatively, informal presentation. So now let's talk about what's kind of wrong with current inference scaling methods. So if we have to kind of take several steps back and think about if I asked you to come up with the most basic inference scaling method possible, you would come up with this idea, probably, of majority voting, which is I'm going to take a language model and I have a question. I'm going to ask the language model this question n times, and I'm just going to pick the most common answer. So this requires no external reward model. It requires basically just a language model and a question. And as you can see in this graph from a Hugging Face blog that came out last year, the x-axis is the number of generations, so just the number of times you're querying the model. And the y-axis is the accuracy of the data set of your method on a Math 500 data set. So as you can see, this is the kind of, inference time scaling curve that everyone wants nowadays. You can kind of see this very general gradual progression up. So as you query the language model more times, the most common answer being your final answer, your accuracy goes up. The next thing you might want to do is say, okay, I could just take the most common answer, or I could have some sort of external model, in this case, a reward model.
Quick question. Yeah. On the previous slide, what was the model you were sampling from?
This is Llama 1B.
Okay, so it's 1B versus 8B. Okay.
Yeah, so the kind of, you'll see these dashed lines actually throughout the rest of the presentation, so I'm glad you asked to clarify. These baseline, the dashed lines that run throughout the graph are baselines. So this is just if you query the model once for every question, and this is the 8B numbers.
Thanks.
So yeah.
One other question.
Yeah, for sure.
What are the assumptions about the form of the answer? I think obviously true false versus multiple choice versus structured answer could have quite different properties here.
Yeah, absolutely. This is actually, a really good question that you asked it, and this is something that you have to be kind of careful of when you read or analyze what a lot of inference scaling methods do, because how they evaluate their answers is very kind of varies from group to group. So in this specific paper, we used math questions. So the questions are just like almost word problems, and there's no multiple choice. You just have to get the correct answer. But in this specific data set, you also have to format them in LaTeX format. So the format has to be something about like, let's say your answer was 3/4. Your answer would have to be \boxed \frac 3/4. So you kind of need to be very specific about how you're returning that format, and different papers manage this in different ways. So in some papers, if your actual formatting does not match the actual answer, you'll still get the point because they'll manually check whether or not it was the correct answer. But in this work and a lot of other works, it's just an exact match. So either you get the answer in the correctly formatted way or you don't.
Okay, thank you.
When you do your one out of it, your majority, essentially you're kind of assuming that the answers that come back are randomly distributed throughout the possible answer space.
Sure.
Whereas what you're really doing is, there's really no reason to believe that, because there could be certain answers that are easier to come to. There are multiple paths that come to the same answer, but they're wrong. So if you compare this to the first one, where if I among 100 samples, one of them is right, but that could be one that's almost impossible to get.
Yeah, exactly. That's why I think this graph here, this is kind of like the gold. This is the gold standard. This is kind of like the highest you can get, because you're totally right. There might be questions where it gets the right answer 1 out of 1,000 times. And so that definitely would not, be unearthed in a majority voting scenario. And the goal of a lot of these inference scaling papers is to be able to get to that very elusive answer. Any other questions? Cool, I'll move on, continue, feel free to interrupt at any time. So yes, this is a majority voting method, as we've discussed already. And the next one is we're going to kind of take a step away from just majority voting, and we're going to say, okay, I could just take the most common answer. I could also have an external model, which in this case would be a reward model, and have that reward model be trained to take a language model and to take a question and an answer and give it a score. So it's important to note this is not an exact verifier. So it's not going to tell you exactly whether or not a question has a correct answer, but it's trained on a variety of math problems, and it's going to give you a score kind of judging how good the answer is. So in best of n sampling, what you do is you ask a language model a question, again, n times, you take all of the n answers, you ask the reward model to score all of them, and then you just choose the answer with the highest reward score as your final answer. And that's kind of a different paradigm of how, like a very simple inference scaling method. And if you want to take it a step beyond this, you can actually combine the last two methods, right? You can do something called weighted best of n, which is, again, you query the language model 100 times for the question. You put all of the answers into a series of buckets, and based on like which ones are the same, and then you provide a score for each model, for each answer. And then you just multiply. So how many times did the answer come up, multiplied by what the score of that answer was. And then you take the combined highest value of that. So let's say, you had an answer that came up 10 times, but had a score of 3. That would have an entire, value of 30, versus you had an answer that came up 4 times, but had a score of 8. That would be 32, and that would be the answer that gets chosen. So this is kind of better. It's best of both worlds scenario, because you're able to harness both how many times an answer does come up, but also you're able to use this external model to kind of guide your choosing process. And you can kind of see in this graph, again, from the Hugging Face blog, where the x-axis is the number of generations, the dashed lines are your baselines, and you're taking a Llama 1B model. The blue one is majority voting, which we've kind of already seen in the previous graph, and the green and orange ones, so the orange line here is vanilla best of n, which is there's no weighted, just you're taking the one with the highest reward score, and the green line here is a weighted best of n. So you're putting it into buckets, you're scoring the buckets, and taking the highest combined value. And so again, these are the types of inference time scaling curves that everyone really wants to see. But this really just tells you that the more number of generations you get, the higher accuracy you can squeeze out of your model. And this is, I think, a very basic baseline that a lot of people compare to in the inference time scaling universe.
Sorry, can I ask a question?
Yeah, of course.
Which model do you use here to score the results?
Sorry?
Which model do you use to score here?
I think it's a Quen reward model. I'm not sure of the exact reward model they used. I can check for you.
But a strong, like a really strong model.
It's a pretty strong reward model. Yeah. But the base model is still a 1 billion parameter model. Also, the reward model is not like a very large model. It's just a model that's been trained on specifically math, so it has pretty strong performance.
Got it. Thanks.
So that's a large number of n. Is there any assessment of how much computational cost, like how many times you're running the model, and like this looks like not very feasible, 2 to the power so many number of generations. So I'm wondering why even this is a plausible alternative.
Yeah, that's a great question. I think so. If you take a look back at the cost slide that I had earlier, querying a 1 billion parameter language model, even 128 times, is still going to be cheaper than querying, in terms of either cost or energy wise, than querying a GPT-01 level model even once. And so if you're looking at it from purely a cost perspective, it actually does make a lot of sense to try and harness open source models, even if you ignore the various logistical reasons you might want to use them for privacy and all that. Just from a cost perspective, it's cheaper to use a small model a bunch of times than it is to use a truly massive model. Like they have like hundreds of billions, trillions of parameters. And so a Llama 1 billion parameter model is minuscule in comparison to the frontier models. And so if you can use small models, even if you have to query them multiple times, it does still end up being cheaper. And also has a lot of other applications, right? You can use them. It gives access to high performance to people who don't have access to closed models. It's cheaper. You can use them on edge devices. There's getting a lot of applications of these smaller models. So it's not a prohibitive cost, I think.
Sorry, but
we still
the
have
comparison.
right? But we still have to count the reward model as well. That's another complexity. But
sorry?
We still have to consider the reward model. It's not just random.
Yeah, absolutely. The reward model is also a relatively small model. So in most cases, it's like a 7 billion parameter model. So still, I think the combined cost is still less than querying a massive model.
Now the performance is worse than the 8B model, so the comparison should be to the 8B model, not to the frontier models.
Yeah, so I think
from a complexity point of view.
Yeah, absolutely. But I think like later on we'll see some graphs that cover it scales like a 7B model to 01 potential. So then you can kind of, that's more accurate comparison. But yeah, that's a valid point.
A quick question that you're doing your experiments on the 1B model, then why is the starting point for a single iteration is lower than the baseline you have for the 1B
Sampling.
model?
She's sampling.
That's a great question. So the line actually here is like a greedy temperature 0 baseline versus in inference scaling methods, because you do want to take advantage of the diversity that higher temperatures would provide. You are having a higher temperature, and thus it's possible that the accuracy would be different. There's some graphs here where it's lower. There's also some graphs where like the accuracy at 1 is a little bit higher. So as long as it's like kind of around the same baseline, I think it's fine.
Okay.
One more question.
Yeah.
In some problems, it's easier to validate an answer than it is to generate the answer in the first place. And but in arithmetic problems, that probably isn't the case. You have to validate an answer. You probably have to do almost as much work as you did to generate the answer. Does that match up with what you understand, or is there something I'm missing here?
So I think like the key, I think, to this is the fact that like reward models have been previously trained on. So the kind of the process to train a reward model is, I think, a pretty extensive process. So you have to get all your math questions, you have to get a bunch of answers, you have to manually score all the answers. But once you've taken all of that data and trained a model that is literally just poised to take in a question and answer and give you a single numerical score, I think then it becomes relatively lightweight, just because all you have to do is give it a question and your answer, and it'll give you a score. So I think the process of training that model is relatively intense and requires a lot of like hand labeled data and all of that. But I think once you have that model and it's an off-the-shelf reward model, so there's a bunch of them just available on Hugging Face, for instance, then it's not that much work on the part of the user because you just get a question and a score. So.
Okay, thanks.
Yeah.
So there was actually, just to chime in on this, there was a very nice talk by Terry Tao and Mark Chen on the question that Murray asked. So I'm just posting it. So they say like that reward models for difficult math problems are not enough, and you would need like really like all the programs that do formal verification. And this is what OpenAI actually uses in addition of reward models. If you have time, it's a very nice talk.
Yeah, I think the like area for reward models is something that a lot of people are trying to study because a lot of these methods are guided by reward models, as we'll talk about later. And so it's important to kind of study like how to efficiently build them, how to build them for different scenarios and all that. Cool. So next up, we're going to talk about a different type of reward model in this, lens of reward models that we're talking about, which is this concept of a process reward model. So as anyone who's been through, elementary, middle school math education can tell you, and their teachers can also tell you because it's been drilled into our minds, the process of showing one's work is just as important as the final answer. You have to have a clear reasoning trajectory, and you want to be able to judge that just as with just as much scrutiny as you would the end answer. You could get the end answer, but if the reasoning trajectory you took to get there is incorrect, you shouldn't necessarily get as much credit. So I think this is where this idea of a process reward model comes into play, because it is able to judge a step-by-step reasoning trajectory. So the reward model has been trained to take in a question, and now instead of a full answer, it's trained to take in a partial answer. So this is obviously filler text, but you can imagine, let's say you have a question, you have step 1, step 2, step 3, and step 4. The process reward model is then trained to assign scores to every single step of the reward model. And you can imagine that this would be useful because you can almost use it as a guide, right? So let's say you're on step 3 and you get a really low score, you can maybe say, okay, maybe I should adjust my thinking for this reasoning trajectory. And so when you have a process reward model, or a PRM, as we're going to call it, you can use it to guide the search to the best possible answer by scoring your partial answers as you generate them and adjusting to the scores as you see them. So it's almost like having a tutor, over your shoulder, or getting live feedback as you reason. It's able to kind of provide real-time live feedback on each of the steps of your reasoning process. So yeah, this provides a lot of value. I think there's a lot of methods that kind of do step-by-step reasoning and score each one. If you have a really low score, we're going to kind of discard that answer. Process reward models, I think, are really valuable to the field of inference time scaling, but they do have, you can imagine a weakness, which is that in the world of process reward models, they're not an exact scoring mechanism, right? In our school metaphor, this would kind of be like a substitute teacher. So you trust them, but you don't really trust them with everything that's going on in your exact field or your exact subject. So you actually do want to take the process reward model scores with a grain of salt, right? Because it's not like, as I mentioned before, they're trained to be exact verifiers for your specific data set for your specific field. Reasoning trajectories are subjective, and these models are just trained to give scores to partial answers, but you cannot necessarily only trust like blindly what these models are saying. So this is where previous methods like beam search falter a bit. So let me quickly just explain what beam search does. Let's say this is our question. What beam search does is I'm going to first sample 5 independent first steps to my answer. So I'm going to ask the language model to generate an answer, but I'm going to stop it after it generates the first step of an answer. Then I'm going to take all of those steps. I'm going to get the process reward model to score each of those steps. And I'm only going to take the top couple answers. I'm going to kind of ignore the others, and I'm going to continue my unrolling trajectory based on the top scored answers. So at step 2, because in this case, nodes A and C had high answers, we're then just going to continue step 2 from this and this. And so, like I said, a lot of current inference scaling methods actually automatically select only the top n partial ranked answers at every step. But the problem here is you're relying completely on the process reward model to determine what is right or not, which, as we have mentioned in our substitute teacher metaphor, is maybe not the most optimal thing to do, right? Because you don't necessarily know whether the process reward model is guiding you correctly. So you can kind of see here, actually, just to kind of give an example of how beam search performs. This is again from our favorite Hugging Face block. You can see that these are the previous trajectories we were looking at. So this is the majority, this is best event weighted. This green one here you can see is beam search. So it performs relatively well. But there is room to push this even further because the current method that we're going with leads to something called reward hacking. So because process reward models are inadequate representations of the ground truth, kind of following them blindly to determine which partial answers you're going to continue expanding, you're going to continue unrolling, leads to reward hacking, where your final output, the final answers at the end of your entire process, are optimized to score really well according to this reward model. But like the reward model is just there to guide your search, right? No one actually cares about the end score of the reward model. You want to get a high accuracy. So in this case of reward hacking, your output is optimized to score very well according to this reward model, but it's not necessarily always useful or correct, which is where our method comes in. So our method, you can enjoy this nice graphic I made, is about particle scaling. Our method is the full title is a probabilistic inference approach to inference time scaling of large language models using particle-based Monte Carlo methods. But in reality, it's just particle filtering for inference scaling. And if people are not familiar with what particle filtering is, I'm going to kind of walk you through a step-by-step, very basic example. This is the math. You can go see the paper if you want for that, but we're going to start with a more accessible flowchart. So we're going to start with a problem. So let's say you have a problem. This is a problem taken from a math exam. A Senate committee has 8 Republicans and 6 Democrats. In how many ways can you form a subcommittee of 5 members that has at least 1 member from each party? So the first thing you're going to do in our process is you're going to initialize n particles. And what a particle is it's just an object that stores an answer so far. So we're going to take our 4 particles here. And the first thing I'm going to do is I'm going to take a step where the step is all the text that a language model generates until it hits this double backslash n delimiter. And if anyone is not familiar, the double backslash n is just like a new line. In the way that we're prompting the language model to answer the question, you ask it to generate a step-by-step answer. So it'll say step 1, da-da-da-da, step 2, more math, step 3, more math, and there'll be new lines in between each one. And so kind of breaking it along the double backslash n delimiter allows you to separate these steps. So each particle is actually going to have a slightly different first answer because we set a relatively high model temperature, and model temperature controls how creative or random a model generations are. So with a relatively high model temperature, it's much more likely that each answer is going to be a little bit different. And in our school teacher metaphor that we're using for this entire talk, you can think of each particle like a new person involved in a collaboration. Everyone's going to have slightly different ideas and bring something different to the table. So let's say these are our 4 first steps. So we asked the language model this answer, and we stopped it after it finished its first step of reasoning. These are our 4 answers. This is just an example, by the way, but we're using this to illustrate how the method works. So these are our 4 answers. The next thing we're going to do is we're going to take our PRM, an off-the-shelf process reward model. We didn't train this. It's just taken from Hugging Face, but you use this to assign scores to each question and partial answer. So these are 4 scores that the process reward model gave to these 4 particles. 0.849, et cetera, et cetera. And the next thing you're going to do is, these scores are great, but we want to use them. And so we're going to softmax the reward scores to get probabilities. So a softmax function just takes a set of numbers and converts them to probabilities. So these are the scores, and these are our probabilities. So each probability in this case actually represents the chance that that particle is going to be evolved in the next step of the process. So what that actually means is we're going to do something called resampling, where you can remember these are our probabilities for each particle. In the next step of this process, every single particle is going to be continued independently from the previous stage's particles with these respective probabilities. So, every particle in step 2 has a 30% chance of being continued from this step 1, an 18% chance of being continued from this step 1, 17.3 of this, and 34 probability of this. And so you kind of realize the difference here between what beam search or a lot of deterministic methods are doing versus the particle filtering method is, in beam search, you're blindly just taking the highest reward scores and only unrolling those, only continuing those reasoning trajectories, versus in this situation, we're sampling. So these 2 answers do have higher scores, and so they will have a higher probability of being resampled, but there is still a smaller chance that these 2 particles, even if they got lower scores, will have the chance to be continued as well. And the benefit here is that you have this kind of balance between exploiting the reward model score and still having that exploitation of the information you've been given, but still allowing for some exploration, given that we know the process reward model is not the end-all be-all of ground truth data. So this is, again, a random example, but let's say, based on these probabilities, this particle is continued from this particle is continued from particle 3, and both particles are continued from particle 4. So the next thing we're going to do is we're going to generate a next step based on step 1 of this, and these both are going to generate different step 2s based on the step 1 of this particle. So each particle is independently, randomly going to select from the previous set of particles with your weight specified. So now you can kind of see each particle is generating the next step. So you can kind of recall this is the step 1 from the previous answer, and we generated a step 2. And in the case of particles 3 and 4, you notice these both are sampled from the same one previously. You can see that up to this point, they're actually the same, but after that, they become different answers. And so this entire process just continues over and over and over. You have a particle generated next step. You use the process reward model to score it. You convert the score to a softmax. You use the softmax to convert it to a weight. And then you resample the particles according to those weights. And you just continue doing this over and over and over until every single particle has generated an end of sequence token and thus finished its answer. So this is a kind of a more complete, graphic of what the process looks like. So again, you have your particles, a language model generates some answers, you have a process reward model that scores them, you convert that to a weight, you resample based on those weights, and you just continue doing this. So just as a note, let's say I have 4 particles. At the very end, your scores, at the very end, you've only actually done, my sister's calling me. You've only actually done 4 complete generations. So 4 particles means your budget is 4 complete generations. 8 particles means your budget is 8 complete generations. Just because you're stopping it step by step doesn't mean the actual contents change. You're just stopping and choosing particles based on that process. Does anyone have any questions based on this process so far? Any confusions? Cool. Yeah, I think the nice thing about this is that it's a relatively simple process, and it makes a lot of intuitive sense, right? You want to take your steps, you want to have scores, and you don't want to be blindly guided by the PRM, but you do want it to allow it to, inform how your search is going to go. So, this is, the more full version with all the math and labels, but you have your steps, you score, you resample, and you just continue doing that until you're done. So we're going to kind of dive into the, I think, pretty cool results that we've been able to get with this method. So we're going to kind of focus on 3 main points. The first one is that there's 4 to 16 times better scaling rate compared to deterministic search methods with challenging mathematical reasoning tasks. So if you look at something like these graphs here, the thing that's important in this situation is not just the accuracy, right? You also want to get there as fast as possible, as someone mentioned. If you have to do it for 128 particles to get to a certain accuracy, that's great. But if you can do the exact same thing with 8 particles or with 16 particles, that's a lot better in this scenario. And so the scaling rate is really important in a lot of inference scaling methods. And you can kind of see the red one is a weighted best of n. The purple line is a deterministic method called DBTS. And the blue line here is our method. And you can see that with the exact same accuracy as around 65, the blue method, aka our method, is able to get there in between 4 to 8 generations. And it takes, the competitor method 64 generations to get there. And you can kind of see this same very accelerated scaling rate across all of the graphs. The next thing that I wanted to highlight is that you have a 1.5B Quen model. So this is a math instruct model that only has 1.5 billion parameters in the entire model, and it's actually able to surpass GPT-4o level accuracy with only 4 rollouts. So you can see well, I actually think I did not include the graph, but you can see that in a graph in the paper and the website, that the 1.5 billion parameter model actually surpasses GPT-4 accuracy with 4 rollouts, which is kind of insane because GPT-4o is a truly massive, massive model. And with only 4 generations and 4 particles, you're able to surpass that accuracy. And again, this is with no training at all. You're literally taking an off-the-shelf open source model and an off-the-shelf reward model, kind of using them to guide each other through the process. And you're able to get very, very high accuracies. And the kind of more buzzwordy result that I think a lot of people have been paying attention to is the fact that you're able to go from a 7 billion parameter model. So this is a math instruct 7 billion parameter model. And you're able to actually reach O1 level accuracy in 16 to 32 iterations or particles. And again, these are really cool numbers because it just emphasizes the discrepancy in size between the models and how simple the process is. No training at all, just off-the-shelf models, and you're able to kind of harness their collective power to scale your
So
performance.
Isha, did you guys do the Quen like 1.5, not the math, like just the regular one, to see what is the discrepancy between Quen models, the math and non-math ones?
So we did 2 kind of categories. One was like small, not math models. We used Llama for those actually, because a lot of people in the community were using those. And then we used the math models to do the math version. So the smaller models of the same size you can see is like the Llama 1B and Llama 8B.
No, I'm just mentioning the Quen models because there are some debates like, or are those data, those models seems like to really, with small iteration of reinforcement learning, to really get very good at math. So I'm wondering, like, if you just take the Quen model base and just allow to do inference time, if it will also scale well.
Yeah,
like without the math instruct, yeah.
Yeah. We didn't test this in this case, but
awesome.
Yeah, it's a good thing to test. Yeah, so these are, I think, very cool results, again, because, of just how pretty the inference time scaling curves are. But why should you really care? I think a lot of people who are involved in the language model community, there's like 15, 50, 100, 200, there's thousands of papers that come out basically every day if you're being hyperbolic. And why should this one be any more interesting than the rest? You're doing all of this, scaling very small models to very, very high numbers without training anything at all. In the past couple weeks or months, there's been an emphasis in the community on how to train better reasoning models. But what this work really emphasizes is that you don't actually need any training or any additional, work on that side of things to be able to get very high numbers. You can actually just squeeze, all of the juice out of these small language models just with this entire process. And so you're able to just kind of discover the potential that the language models have just by kind of intelligently navigating the search space. And coming back to the power of open source models themselves, if you follow results like the ones that we've talked about today, you can get really, really strong results for a variety of applications, all while kind of keeping your data secure, keeping your costs way down, and even maybe allowing you to use, your own small customizable models if they're very domain-specific applications. And so, there's, like we said in the beginning of the talk, really strong promises of using open source models. And if you can get the open source models to perform at a very high level, then you're kind of golden. And I think what this method and a lot of other inference time scaling methods allow you to do is show that you can actually scale small models to very large potentials. Some things for the future. So inference time scaling is great. The graphs are very pretty. There's very high numbers, but what can you actually do with that? You can maybe use the partial and full reasoning trajectories generated by this method as training data to make the models inherently better at reasoning. This is something that a lot of people are doing across the board now, but using these, you can imagine, right, that once I have my entire particle filtering process has been completed, I now have a very, very extensive reasoning tree, right? Let's say I have 4 particles at every step. I know exactly which particles got chosen, which particles didn't. I can navigate that entire tree to generate a ton of reasoning trajectories completely automatically. So there's no kind of human intervention necessary. You can just convert the entire process to a giant data set of reasoning trajectories. And then from more of a logistical and systems perspective, right now inference scaling takes time because you do need to query a model, let's say 128 times, 64 times. So the folks at VLM and a lot of other open source providers are doing a lot of great work to optimize it and make that process cheaper. But yeah, I think, the field of inference scaling is really, really crucial, I think, both just in and of itself to scale small models, but also as a springboard then for a variety of other applications. And I think this method is a cool, very simple and elegant way to really take the most advantage of small open source models. And yeah, thank you everyone for listening. We have a website that has a video, and if anything was confusing, there's an animation that kind of walks you through the process, and the paper and everything. The code is all on there. So thank you for listening. And does anyone have any other questions?
Awesome. Thanks a lot, Isha. Any questions?